it streaming phone or not yet? No, it is streaming. Joseph, maybe you take over.
Sorry?
You take over.
Okay, should I start then?
Yeah.
Okay. So, welcome everybody to the fifth lecture by Narayanan from IISc Bangalore. And he will, I think, finish today the series of talks which he has been giving so far. And the title is Harish-Chandra's proof of Plancherel theorem for SL2R. So over to you, Naru.
Thank you, Jotsaroop. So today is the final lecture in this series of talks. We will prove the Plancherel theorem for SL2R via Harish-Chandra's methods. So there are quite a lot of computations involved in this case, even in this simple case of SL2R. Most of it is just calculus. Okay, so it is elementary, but at the same time, the proofs are not entirely trivial. There are some things to be done. So what I will do is I will give a overview of what Harish-Chandra's philosophy is about the Plancherel theorem, and then we will look at SL2R, and so many things will be assumed. It will not. I will not do all the computations in this lecture. It's not suitable. These lectures are not suitable for all those computations to be done. But the final step, maybe two steps, we will see in detail. Okay. So let us see. So we are looking at a semisimple Lie group. Okay, so SL2R is the group we have been studying, but in general we are looking at semisimple Lie group connected, non-compact, with finite center. So this is a rich class of groups to start with. You can of course take SL2R as the example. Okay, we are not going to prove anything in this general setup. We are only going to look at SL2R, but I want to give you an idea about what it is we are doing. So this is the Lie algebra of G. We take a Cartan subalgebra. So H would be a Cartan subalgebra. So which means maximal abelian. Okay. Now associated to the Cartan subalgebra, there is a Cartan subgroup of the G. So let H contained in G be the centralizer of H. So that is the Lie algebra H in G. Okay. So this will be the Cartan subgroup associated to the Lie algebra H, and this can be disconnected. And that these things matter when you do various things. But in our case, we will see a disconnected Cartan subgroup, but it's quite simple, so there is no serious issue. Now what happens is associated to each such Cartan subgroup H, there is a function. Let's call that d sub h. Okay, this is called the Weil denominator. So again, this is also quite explicit. Okay, once you know the root space decomposition with respect for G and H, you can actually write it down as a function. Okay, called the Weil denominator, and assign So let's call that epsilon h. So dh is a function on the group h, right? So this is always equal to plus or minus 1. Okay, so depending on the value of h, you may get plus 1 or minus 1. So that's not very. I mean, again, this has to be defined. It takes some effort. Then there are orbital integrals. Orbital integrals over g by h for a suitable function f. So f you can take to be a compactly supported smooth function, right? It's the infinity function, so everything will be well defined, and that is given by f sub f super h. Okay, so associated to each Cartan subgroup there is a orbital integral. Okay, so that's what I'm going to define. It's a function on h. So for each h, f sub f at h equal to epsilon h at h. So this is just plus or minus 1. DHH, this is the wild denominator, some function. For SL2R, we will write down these things explicitly. Integral over g by h, f of gh, g inverse, d of gh. Okay, so this is the g invariant measure on g by h. Okay. So this is like Abel transform. Okay, so like Abel transform in the k by invariant. Anyway, we'll write down these things very explicitly. Okay. So there are three key steps or ingredients in the Plancherel theorem. So three main steps, let's say. Okay, one is the orbital integral, of course. Then rather strong theorem by Harish-Chandra. So let me write down theorem by Harish-Chandra. If H is a Cartan involution stable subgroup, Cartan subgroup. So there is a Cartan involution for G, and so that's generally called theta. If your H is theta stable and maximally compact. So some of these things I'm not going to define because in our case SL2R we know these things explicitly. Okay. Then there exists C constant not equal to 0 such that some differential operator, so that's what we call del of f sub f h. So remember the f sub f h is the orbital integral corresponding to the Cartan subgroup H at E. The identity is some that constant times Fe. Okay, where del is a differential operator. Okay, is a differential operator explicit. Okay, again, once you know the root space decomposition of G with respect to H, you can write down this as an element in the universal enveloping algebra of H. Okay, so this will belong to the universal enveloping algebra of H. Okay, so it can be explicitly written down. So this is one result. Two is if phi is in G hat, so that is a unitary representation. Theta pi f. So what is theta pi f? This is trace of pi f. Okay, remember pi f is the Fourier transform, right? Integral over G f g dg. F g pi g dg. right? That is the Fourier transform. And trace of that will be f integrated against a locally integrable function. In other words, trace of the representation is a locally integrable function. This is the rather strong theorem due to Harish-Chandra again. This particular quantity theta pi f, so that will come up in the inversion, right? So think of inversion for compact groups and so on. This is the quantity that will come up. So this can be written as as Euclidean Fourier transform of a certain function. Okay, so certain functions multiplied with f sub f h. Okay, so this roughly in the Euclidean case would be the n-dimensional Euclidean Fourier transform is the one-dimensional Euclidean Fourier transform of the Radon transform. Right? In the K invariant case, you can write the spherical transform as the Fourier transform of the Abel transform, Euclidean Fourier transform of the Abel transform. Okay, so this is similar to spherical Fourier transform equal to Euclidean Fourier transform of the Abel transform. Okay, that's a particular case of a orbital integral and this. Okay, so third one is well, this is innocuous. I mean, it sounds very innocent. Integration by parts and boundary values of f sub f. Boundary values of f sub f is a crucial thing. So integration by parts and boundary values of f sub f h. Okay, so these are the three things one needs to complete the proof of the Plancherel theorem. Okay, so now this is all very general, right? So now we are going to stick to SL2R and we will do everything for SL2R. Okay, so I've divided the whole proof into several steps. So I'll not give the proof of any of the steps except the last two. Okay, so now let's look at G equal to SL2R. So in the when one looks at these Cartan subalgebras and Cartan subgroups and so on, Cartan subalgebra, you take a Cartan subalgebra, look at conjugates of that they are also Cartan subalgebras. Okay, so one has to choose Cartan subalgebras which are not conjugate to each other. In the case of SL2R, there are two of them. So that's like choosing representatives of Cartan subalgebras, right? So there are two of them. So for SL2R, there are two non-conjugate Cartan subgroups. Okay, so that's not very difficult to prove. So first one is A. Well, this A is different from the A we have been using. So I'll comment upon that right now. So A sub T, where A sub T is the matrix. This is something we know, e to the t 0, e to the minus t. Okay, but t belonging to R. Okay, so there are two of these things, right? This is a disconnected group. Disconnected. Okay, so that is why the Cartan subgroup can be disconnected. So one word of caution is this is different from the A we used earlier. Okay, the connected component containing identity of the current A will be the previous A, right? The previous A meaning A in KN and KK decomposition. That A is just one piece of this A. Okay, the current A is a disconnected one. So A in this lecture would stand for this plus or minus AT, where AT is that matrix e to the t 0, 0, e to the minus AT. And the Haar measure on Our measure on A is normalized, so that if I look at integral over A FADA, this is going to be, so there are two pieces, right? So it is half integral over R f of AT dt plus half integral over R f of minus AT dt. Okay. Now that is the first Cartan subgroup. The second one is the maximal compact K, SO2, and this we know K theta. So this is written as cos theta minus sin theta cos theta. Right, theta in R of 0 to pi. Okay, so that is a compact Cartan, and the other one is non-compact. Okay, so there are two such Cartan subgroups. Now, also remember that this is maximal compact. Right, so remember the theorem that if you have a maximally compact Cartan algebra which is theta stable or whatever, then there is a differential operator which brings back f at identity. Right, we will use that. But before that, let me write down the orbital integrals. Okay, so orbital integrals. So recall that orbital integrals require the Weyl denominator and that epsilon h, right, which is plus or minus 1. Okay, so all this is very explicit in the case of it. I mean, it's explicit in all cases if you know the root space decomposition. In the case of SL2R, everything is much simpler. One can write it down. Okay, so I'm going to write down these expressions. So we'll take an f which is Cc infinity g, and we'll also assume that it is conjugate invariant. Okay, so that means f of kx k inverse equal to f of x for every x in G and k in K. Well, it is enough to look at these things. Okay, why is that? Because when we write down the Plancherel theorem or inversion, it will be clear. All the terms that appear in the inversion are conjugate invariant. Okay, so for example, the character, right? The character of a representation is conjugate invariant, right? Because it's trace of something. So when I conjugate, I'm conjugating the matrix or the operator with two other one invertible operator, right? So the trace will be the same. So it's enough to look at these kind of functions. Okay, so we'll assume that. So there are two non-conjugate Cartan subgroups. So there are two orbital integrals. So the first one over G by K. So that is associated with K. So this is f sub, so we'll denote it by f sub f k, right? F sub f h, where here h is k, and it is defined on the Cartan subgroup. So that is k theta. So I should tell you what this is, right? So this is simply e to the I theta minus e to the minus I theta. This is the Weyl denominator, integral over G by K, f of G k theta G inverse dg. Okay, so that is how the orbital integral is defined, and over G by A, that means associated with A, that is the non-compact Cartan subgroup, f sub f A at, I should tell you at AT, right? But there are two such things, so I'll write it at plus or minus AT. This is a slightly more involved expression, but if you have seen the Abel transform, you will recognize it as the Abel transform. Okay, so plus or minus e to the t integral over G by A. So remember, G is K-A-N, so it is K cross N, right? So when I look at G by A, roughly it is K cross N, and f of K plus or minus AT N K inverse dkdn. Okay, so dkdn is the measure on G by H. H here is A, right? But remember the invariance for F. So these K's in these positions will disappear, right? So that is a much simpler expression. And so integral over K will also go. So that is just plus or minus e to the t integral over n f of plus or minus at times n dn. Okay, so this is what one calls the Abel transform in general. It's integral over n, right? So that is the Abel transform. Okay, so we have the orbital expressions for the orbital integrals. Okay, now we need character formulas. So that is the next set of formulas we will write down. So the computing the orbital integrals is not all that difficult, but you need to know the rate space decomposition. So character formula, this requires some work, but one has nice expressions. Okay. So for pi in G hat, a unitary irreducible representation of G, there exists theta pi. This is a locally integrable function. Locally integrable function with some regularity and so on. Okay, but that's a deep theorem due to Harish-Chandra, such that for every psi in CC infinity G, theta pi of psi. So what is this? This is trace of pi psi, which is the Fourier transform. So let's recall that pi psi is the operator defined by integral over G psi G pi G dg. Right. So when I take the trace goes inside and it is psi G integrated against trace of pi G, right? And trace of pi G is given by this locally integrable function. Okay, so I mean you have to actually think of it as a distribution, but it turns out to be a reasonably smooth function on G with certain properties. Okay. Okay. Now what happens is when psi is CC infinity, this is a trace class operator. So trace of that makes sense. Okay. And that is given by psi integrated against some function. So so this is what we need to compute for SL2R for all those representations. Okay, so let us compute. Let's write down that. So first one, for n in n, theta comma t in R, we have. So remember the representation. We have the discrete series which contains holomorphic discrete series, that is dn, and anti-holomorphic discrete series, that is dn minus 1. Then there are principal series, two principal series, right? Pi lambda and pi lambda minus. Then complementary series and the trivial representation, they don't appear in the Plancherel theorem. So we don't have to compute the characters of that. So we have theta n plus 1 of k theta. So theta n plus 1 is the character of dn direct sum dn minus 1, right? The dn plus 1 direct sum dn minus, right? The holomorphic discrete series and the anti-holomorphic discrete series. So this can be written as e to the in theta minus e to the minus in theta divided by e to the I theta minus e to the minus I theta. Remember, this e to the I theta minus e to the minus I theta is the wild denominator that came in the definition of the orbital integral, right? And theta of n plus 1. So I need to know what these characters are restricted to each Cartan subgroup. So k theta tells me what is it on the compact Cartan subgroup, and on AT, so that is the non-compact Cartan subgroup, we have a slightly more complicated expression. So I will write it down, minus 1 to the n plus 1. So that is just the sign. Then I have e to the nt. These are very nice functions. Okay, e to the nt 1 minus sine t plus e to the minus nt 1 plus sine t. Sine t meaning signum, the sine function, right? Modulus of e to the t minus e to the minus t. Okay. So the while denominator here is modulus of e to the t minus e to the minus t. That is not what appeared in the orbital integral. Okay, because there is a change of variable involved, which is what makes it into e to the t times integral over n. That is what happened with orbital integral over a. Okay. So this is one set of character formulas. Two, so that is for the discrete series. Now we need to know the same formulas for the principal series. Okay. So theta lambda, so that is the character for pi lambda of k theta equal to 0 equal to theta lambda minus k theta. So the principal series characters will vanish on the compact Cartan subgroup, and theta lambda of plus or minus at. So on the other Cartan subgroup, which is A, this has a nice expression, e to the lambda t plus e to the minus lambda t divided by modulus of e to the t minus e to the minus t, right? And theta lambda minus of plus or minus at. So that is the next set of principal series. This is minus of the same expression. So I'm not going to write it down again. Okay. So these are very nice functions, nice formulas. Now we can write down the theorem. Okay. So theorem for f in C infinity of G will, of course, assume that f is conjugation invariant. I'm not going to write that again. We have, of course, in the proof we assume f is conjugation invariant, but the theorem is true for all functions, right? So 2 pi fe, and then we have a rather long expression. I'm going to write it down. Summation n equal to 2 to infinity. So this gives me the Plancherel measure. Okay, n minus 1 theta of theta n f. So theta n f, remember, that is just the trace of the corresponding representation acting on f, right? The Fourier transform of f. N minus 1 is the weight, so that is the discrete part of the Plancherel measure, plus 1 by 4 integral over r theta lambda f. So this is the f integrated against the principal series, right? That is theta lambda f times lambda tan hyperbolic pi lambda by 2 d lambda plus 1 by 4. So there is the other set of principal series, that is theta lambda minus of f lambda cot hyperbolic pi lambda by 2 d lambda. Okay, so these two functions are called the Harish-Chandra C function. Harish-Chandra C function. If you are looking at only k by invariant case, you will have only this function. Okay, the discrete series and the principal series, the other set of principal series will not come up. And this would be the spherical Fourier transform. Okay. Okay, so proof of this we have divided into several steps, and I will write down those steps. There are quite a lot of expressions to be written because you want all these functions to come in finally as the Plancherel measure. And we will use all the formulas we have, the orbital integrals and the character formulas, right? So proof step 1. So remember that K is maximal compact. Cartan subgroup. So the first theorem I wrote down, that there is a differential operator acting on the orbital integral corresponding to a maximally compact Cartan subalgebra, gives me f at identity multiplied with some constant c which is non-zero, right? So we get, so that theorem applied to this particular case where k is, so k, remember, is SO2. We get, so limit theta going to 0 d by d theta of f sub f k. So that is the orbital integral corresponding to the Cartan subgroup k at k theta equal to minus 2 pi I Fe. So minus 2 pi I is the constant C, which is non-zero. Okay. So this is of course we are using a very major theorem due to Harish-Chandra here. All right. Now you see I have written limit because this f sub f of k, right? The orbital integrals over A are much better behaved. Orbital integrals for K have problems at problems, meaning at boundary values there are issues. So one has to take limits and so on. Okay, so that is why I have written limit theta 1. Now step 2. Step 2 is connecting the orbital integrals and the character formulas, right? So I will write down that as using Euclidean Fourier transform. So step 2 is f sub f A. So this is the orbital integral with respect to A at AT. This is equal to 1 by 2 pi integral over R theta lambda of f, theta lambda minus of f plus theta lambda of f. So these are functions of lambda, right? This is f integrated against the trace of pi lambda and trace of pi lambda minus. And these are functions, right? These are functions of lambda. You take the Fourier transform of that, Euclidean Fourier transform with respect to lambda, right? At the point t. So you will get the orbital integral at the point at. Similarly, whenever I write down something for at, there is a formula for minus at also, right? So f sub f a, because these are disconnected things, so that has to be written separately. But the formulas are very close to each other except for appropriate sign changes. Okay, so theta lambda minus f. Instead of plus, we will have minus. That's the only difference. Okay, e to the minus I lambda t, d lambda. Okay. So if you have seen the k by invariant analysis, theta lambda minus f will be 0 if f is k by invariant. You will have only the theta lambda f, and then you will see that this is the Abel transform and the Euclidean Fourier transforms will give me the spherical transform. That's precisely this formula. Here we have two sets of principal series. Okay, so there are two such formulas. So now we can go to step 3. So these proofs require, so step 1 and 2 require some work. Step 1, we are using a theorem due to Harish-Chandra. Step 2 requires some work. Okay. But what remains is once you find these formulas for characters and so on, what remains is just calculus. So step 3, now we have written down the orbital integrals using the characters for the principal series, but these are orbital integrals with respect to A. Similarly, for discrete series, we have some formulas, right? So I should write down that as well. So for n in n, we have, so this is a longer expression, n times theta n plus 1 f. So remember, theta n plus 1 is the character of dn plus 1 plus direct sum dn plus 1 minus, right? The holomorphic and anti-holomorphic direct sum. This is equal to minus 1 by 2 pi I integral 0 to 2 pi e to the I n theta plus e to the minus I n theta df k by d theta at k theta. So remember, f sub f k is the orbital integral corresponding to the compact Cartan k plus half integral over r. Now comes all these functions which we need, e to the minus n mod t, signum function of t, times df sub f a divided by dt at at dt. And whenever I write something for a sub t, there is something for minus a sub t also. So that gives me plus minus 1 to the n. So this is essentially the integral just above, except for some sign, right? Sin t df sub of a by dt at minus AT dt, right? That's only. So these things will come in pairs always, okay? So there is a dFFA at AT and minus AT, and two such integrals will always. But you see, this is a nice formula already, because this writes various things. So look at the first expression, that is 0 to 2 pi to the in theta. That's the Fourier coefficients of the derivative of f sub f at k, right? So when I said Fourier analysis on the Cartan subgroups, here one of them is the compact one, which is the circle, and you have Fourier series there. The other case, you will see Fourier transform. You already saw here the Fourier transform coming in. So that we'll have to use that. Okay, so step 3. Now we are in a position to put together all this to prove the inversion. Okay, so step 4. So this is the first expression for. This is not exactly the Plancherel theorem. It is it's the first approximation, if you like, for f of e. Okay, 2 pi f of e equal to, so huge expression, n equal to 1 to infinity, n times theta n plus 1 f. So these are the expressions that is the first expression appearing in the Plancherel theorem itself, right? So that is there already, plus half f sub f a at a0. A0, remember, is the identity matrix, right? At is e to the t 0 0 e to the minus t. When t is 0, it is just the identity matrix, plus f sub f a at minus a0. Minus a0 is the minus identity. So if you remember, I mentioned in the beginning that the boundary values of the orbital integrals, those things become important. These are precisely that. Okay, so when you look at A, you have that point 0 as the boundary of one of the Weyl chambers, and the boundary values are important. Okay, so that has to appear, and then you have minus half summation n equal to 1 to infinity integral over r e to the minus n mod t. So all these things you saw in the previous formula, sin t df sub f a by dt at at. And as I said, keep saying, whenever I write something for at, I should write something for minus at as well. So n equal to 1 to infinity integral over r e to the minus n mod t. Yeah, there is a minus 1 to the n here, sin t, the signum function, times df sub f a by dt at minus 8, right? So let us prove this. So we will use all these formulas we have. We put together these formulas. We are going to get the first expression for f at identity. Okay, so proof. So I have to keep writing some of these expressions, which may take some time. Okay. So first we use step 3. By step 3, well, what is step 3? Let us go there. Step 3 says n times theta and plus 1 f equal to some expression. Okay, well, let's forget the expression for the time being. And here we are summing these expressions, right? So I need to sum these expressions with respect to n. Now, if you look at this, when I sum with respect to n, what am I going to get? I'm going to get all the Fourier coefficients of df f sub f k, right? That is what I will get. But look at n equal to 0, there are 2 of them, right? So I'll be doing the Fourier coefficient I'll be adding the Fourier coefficient at 0 2 times. Okay, and there is a minus 1 by 2 pi in the beginning. Okay, so keep that in mind. You will get, so by step 3, summation n into theta n plus 1 f n equal to 1 to infinity becomes minus 1 by 2 pi I summation over, now I'll write it as k over z, because I have e to the in theta and e to the minus in theta, and I'm running over n in n, right? So I'll get everything in z, except that 0 will come twice, right? So that I have to adjust. So this is simply integral 0 to 2 pi e to the I k theta df sub f k by d theta of k theta d theta, right? Plus, so this is the adjustment we will be doing at the 0th when k equal to 0. That is simply 0 to 2 pi. So that is the extra thing which we are cancelling, right? df sub f k by d theta of k theta d theta, right? That's the Fourier coefficient at 0. Okay, plus the remaining terms. Okay, I'm not going to write down that whole thing now because that's not needed right now. Okay, see, the remaining term will exist as it is. Okay, let's go here. When I add this expression with respect to n, the first two we have added, the remaining as it is, right? The remaining as it is sits inside the formula here also, right? Oh, what does that mean? Just give me a minute, okay? Something happened to my OneNote, so I'll close it and then. Yeah, I think we are okay. Now let me share. Yeah, okay. We should be fine now. So the remaining terms will stay as it is. We are only summing up that, okay? So now if you look at these two terms, so this is simply the usual Euclidean Fourier analysis. So these two will be sorry, the second term. So let's look at the second term on the right. Second term on the right. So that is this 1 by 2 pi I integral 0 to 2 pi df sub f k by d theta of k theta d theta, right? This is simply the Fourier inversion at 0, right? If you like, but as I said, this f sub f has some problems at boundary points. So one way to do this would be, because since we don't know the singularity, because I didn't discuss the singularities and so on, one looks at these functions, one knows what to do. Okay, so this becomes you, instead of integrating from 0 to 2 pi, you integrate from 0 to pi and then pi to 2 pi. Okay, this becomes sorry, minus 1 by 2 pi I limit of theta going to pi f sub f k of k theta, right? That is just the usual fundamental theorem of calculus, minus limit theta decreasing to 0. So there are problems at 0, pi and 2 pi. Okay, so that is why one does this limiting business, plus minus 1 by 2 pi. The other part, which is limit of theta going to 0, f sub f k at k theta minus limit theta decreasing to pi f sub f k at k theta. So instead of 2 pi, I have written 0 there. Okay, and this one knows that this is equal to minus 1 half at f sub f a at a0. A0, remember, is the identity matrix, plus f sub f a at minus a0, which is the minus identity, right? So see, this is an important expression, you are looking at f sub f k, that is the orbital integral with respect to the compact Cartan, and then the boundary values are actually the orbital integral with respect to the other one, right, with respect to A. So that is a that's an important relationship. And the first term on the right, so what is that? That is minus 1 by 2 pi I integral over k in z integral over 0 to 2 pi e to the I k theta df k by d theta k theta d theta. So, well, what is this? You are writing the Fourier series of df sub f k at 0, right? That is what this is. Of course, you need to know that the inversion works for this function. So this is a reasonable function for which Fourier inversion works. Okay, so for which Fourier inversion works. Okay, and so this would be simply I times dff k by d theta at the point E, right? At the point 0, right? That is E by the Fourier inversion, right? But remember this, the step 1 tells me that there is a differential operator acting on f sub f k, which gives me f at identity. So that is just 2 pi f by step 1. Okay. So that proves step 4. Okay. So let's go back just to make sure that we have got the expression. So step 4 is 2 pi fe is sum, right? So we looked at this and we proved that we have these terms, right? That is something here, and whatever is here is already here, which is summed up with respect to n. Okay, there is nothing new there. So only the compact Cartan is taken care. Okay, so now we'll look at the other part. So that is the final step, but this requires some computation. Okay, I should be able to do this in the next 10 minutes. So step 5. So let's say final step. Half f sub f a0. So remember this, and half f sub f a minus a0 was there already in the previous formula. Minus half summation n equal to 1 to infinity integral over r e to the minus n mod t sin t. All these formulas are there already in the previous one. dffa by dt at at dt. So whenever I write for something for at, I should write the similar expression for minus at. So that is plus half f sub f a at minus a0. So remember, these two terms were already there, right? Minus half summation n equal to 1 to infinity minus 1 to the n. This is the expression with minus at coming in the argument, right? Sin df sub f a by dt at minus at, right? These expressions are same except for a and minus. Now, what is the big deal? This has to be connected to the characters of the principal series. Okay, so that is precisely what we are doing, and this is pure Fourier analysis. Integral over r theta lambda of f lambda tan hyperbolic pi lambda by 2. So that is how these functions come in. Okay, plus 1 by 4 integral over r theta lambda minus of f lambda cot hyperbolic pi lambda by 2 d lambda. So once we prove this, we can put all this in the previous step. Wherever these huge sums are there, that will be replaced by whatever we want, which is the lambda tan hyperbolic pi lambda, lambda cot hyperbolic pi lambda, right? Those are the C functions of Harish-Chandra. Okay, so let's prove this. To prove, start with start with expressions for f sub f a at at. Remember this is like the Abel transform, and you had the Fourier transform of the characters, right? And f sub f a of minus at in terms of theta lambda f and theta lambda minus f in step 2. Right, step 2 was just calculating these things, right? So I'll write it down, okay, because it's difficult to remember all these expressions. So f sub of a at t was half integral over r theta lambda minus f plus theta lambda f e to the minus I lambda t. Remember what I said, that the Fourier transform of the spherical transform is the Abel transform, right? So similarly, you had the formula for minus at, that is half integral over r theta lambda minus f. The difference was that here there was a minus, and again you take the Fourier transform e to the minus lambda. Okay. Now this implies if I differentiate this equalities at plus or minus at, right? This is differentiating this with respect to t. So when I differentiate with respect to t, I have a lambda coming down, right? That is again Euclidean Fourier analysis. So this I can write as I will write as h plus or minus hat at t, right? Because there is a e to the I lambda t. So it's Fourier transform of something, okay? But what is h, where h? So this is just for instead of writing the whole expressions again and again, h plus or minus lambda is equal to minus I lambda by 2 pi theta lambda minus f plus or minus theta lambda f, right? So lambda times some other function in lambda, right? Its Fourier transform will be the derivative of the Fourier transform of the function. That is all is written there, right? Okay. Now, so hence, so what do we get? We get the first piece of the formula, hence integral over r e to the minus n mod t sin t. So all these things was there in the previous formulas, right? When we wrote down 2 pi. And we remember that we had these characters, df, these expressions df by dt, t, and this is nothing but, so let me write plus or minus so that I don't have to keep writing two expressions. This is nothing but h plus or minus hat at t. Okay. So I have some function integrated against the Fourier transform. The Fourier transform can be put on the other function, right? So this is nothing but this is equal to minus 1 by pi integral over r, and anyone who has done first course in Fourier analysis knows how to compute the Fourier transform of this. You will get the Poisson kernel, right? So that is just lambda square by n square plus lambda square. So n comes because you have e to the minus nt times the hat goes to the other sides, right? So h will be just this function, right? So that is okay. I'm missing a lambda somewhere, right? Anyway, I'll not bother too much about this. Plus or minus theta lambda f t lambda. Okay. Also, similarly from the, so this is a EC computation. So this I will not bother about justifying. Some step 2 FFA at A naught plus FFA at minus A naught is integral over R theta lambda minus F d lambda. Okay, that's a simple computation that I will not. So now we have all the computations done. Okay, so LHS in step 5 Okay, so what are we trying to prove? We are trying to prove that this mess is equal to the right hand side, right? This mess is what is there in step 4, and so this mess can be replaced by whatever we want. Okay, so if I add this and this one, I have one integral, which is the last one I wrote. These things are taken care by Euclidean Fourier transform, right? Because this was the h plus hat and this was the h minus hat or whatever, and the hat went into the other side, we got the Poisson kernel, right? So you put together all this, you will get equals 1 by 2 pi integral over r theta lambda minus f d lambda. So that is the f sub f at a0 and f sub f at minus a0 plus 1 by 2 pi summation n equal to 1 to infinity integral over r lambda square by n square plus lambda square theta lambda minus f plus theta lambda f d lambda. Okay, and and similarly for the other 1 by 2 pi summation n equal to 1 to infinity minus 1 to the n integral over r lambda square by n square plus lambda square theta lambda f, but there is a minus in the d lambda, right? Okay, so now you can simplify this to get, so if I add these two, because of this minus 1 to the n and there is a plus and a minus here, some things will get cancelled, some things will get, so for n equal to even, only certain things will survive. For n equal to odd, only certain things will survive, right? So you sort of group them up, you will get 1 by 2 pi summation n in z even integral over r lambda square by n square plus lambda square theta lambda minus f d lambda plus 1 by 2 pi summation n in z, but n odd integral over r lambda square by n square plus lambda square theta lambda of f d lambda. Okay, so now we are done, because so this is simply 1 by 4 integral over r theta lambda minus f. If I sum up this series, I'm going to get chord hyperbolic. So lambda chord hyperbolic pi lambda by 2 plus again 1 by 4 integral over r theta lambda of f. If I sum this, the odd ones, I'm going to get lambda tan hyperbolic pi lambda by 2. Okay. So that is all. So because, so I'll write down this, because summation n in z even lambda square by n square plus lambda square is equal to lambda chord hyperbolic by lambda by 2, etc. Similarly for the tan. So you put together all this, we have the inversion. So that completes the proof. Okay, so I'll stop here.
Okay. Thank you for a really nice talk. Are there any questions? There is something in the chat.
Yeah, that was Ajit's comment. Yeah. Yeah, but there is no question.
Yeah, it's not a question, it's a comment.
Okay, so I'll stop sharing then.
Okay, then I'll leave it to then I'll leave it to Devendra to finish. I think he would like perhaps.
Thanks, Jotsaroop, for coming to chair the final talk. It was very comprehensive, as Professor Ajay Tuppal thinks so. We are looking for the better notes of these talks. Let us see when it is possible.
Yeah, we'll
Thanks,
see.
Professor Narayanan, for this series of lectures. And share the slides and try to
Yeah,
get us the
I'll send these
better.
notes. Yes.
Yeah, thanks.